Okay, so yeah, good morning everyone. Last class we saw this division problem and we saw an NC2 algorithm for division. So essentially the idea that we explored last time was we reduced division to the reciprocal problem, because essentially it is computing the reciprocal of an n bit number and then multiplying it with the dividend. And the way that algorithm worked is we use the Newton-Raphson's method to approximate to approximate any function, and then we saw that we can use that idea in log many iterations. We can get a n bit approximation of the reciprocal, okay. And in each iteration the way it works, we need multiplication, so it needs some log n depth, okay. So that is why we get a NC2 algorithm. So now the question is, can we do better than NC2? I mean, of course, yeah, NC2 means log square, so can we bring down the depth below log square, okay. So this is going to be our agenda for the next couple of lectures. So what we will prove is the following result, that division is in NC1, okay. So this is actually a very strong result, and this is actually a quite a non-trivial result. So this was shown by three scientists, Paul Beam, Cook and Hoover, okay. In yes, same Cook as Stephen Cook, yeah. So he actually had he actually had a lot of work in circuit complexity as well. So he explored these bounded depth circuits, and not just this work, there are other works also that he has in circuit complexity which are quite pioneering. I don't know, so maybe we might look at some of his works later on also, but essentially the same Cook, and this result was shown in early 1980s. I think it was 83 or something like that, yeah. So anyway, so the idea is it's actually a combination of a lot of ideas, but essentially it uses a lot of non-trivial stuff from number theory, okay. Some of those facts, of course, we will try to prove. I will try to give you a proof of those things, but some of those we will just assume that they are true, because the proof itself is quite non-trivial. If you are interested, you can of course look up the proof from any book on number theory, or even some online resources, but we'll see when we come to it, okay. Okay, so this is going to be the agenda. So now let's try to let's try to define a few things. So first of all, just to recall, so the division problem was to formally define it, given two n bit integers x and y. Let us say we want to compute the quotient, okay. We will also look at a few other problems. Powering. So what is the powering problem? So given an n bit integer x, compute the powers. So basically compute x to the power 0, which is nothing but 1, x to the power 1, x to the power 2, so on, let us say till x to the power n. So we will compute the binary representations of this, okay. And just to mention, so like for example, x to the power n. So, how many bits will x to the power n need? Okay, so x to the power n would need in the worst case it can be as large as n square bits, okay, because x is n bits. So, we will assume that for each of these we keep a space of 2n square. Okay. So, we assume that each of these is a 2n square bit string. Okay. You can append it with zeros if it is less than that. Of course, it will be less than that. So, you append it with preceding zeros. The third problem is iterated product. So, we have seen iterated addition and we have seen single multiplication, but we will let us call it iterated product or iterated multiplication. So, this is given n bit integers x1 to xn, let us say, we want to compute the product of all these numbers. Okay. Now, why are these problems interesting? The reason they are interesting is because what we will show is that, so of course, this is the goal, we want to compute this, but what we will show today is that these two problems are equivalent in some sense. Okay. So, it is enough to compute powering to get this, and if you look at the problem of powering an iterated product, powering is essentially a special case of iterated product, right. So, essentially if you, what we will show is that if you can solve iterated product, which means you can solve powering, and by the reduction that we will give, you can solve division also, and we will actually show reductions in the other way also. We will show that actually division also, powering also reduces to division, and this maybe later on we will show that powering also, iterated product also reduces to powering. So, that is actually quite a non-trivial thing, which says that, well, if I want to compute iterated product of n bit integers, it is enough to compute powers of some number. Okay. So, that is a little bit maybe, well, not very counterintuitive, but it is a little bit non-trivial, but we will also see that reduction later on. So, essentially the point is all these three problems are equivalent up to some notion of equivalence. So, what is that notion? So, let us define that. So, first I will define what is log space uniform. Okay. So, log space uniform NC1 So, what is log space uniform NC1? So, NC1 we have seen is the class of functions for which there are log depth circuits of bounded Fano having polynomial size over AND or AND not, right. What is log space uniform? Now, suppose, so I think I briefly mentioned this also last time, that suppose these circuits are now also computable efficiently. So, when we talk about NC1, we do not talk about how these circuits are obtained, we just say that if there exists a family, that is it, that is good enough for us. But how can we obtain such a family? So, now let us say if this family can be computed efficiently, then we come to this notion of uniformity, okay. And let us say if this family can be computed in log space, then we call it as log space uniform. So, what is log space uniform? So, log space uniform is the class of functions for which there is a NC1 circuit family, let's call it as Cn, so it's an infinite family such that there is a log space Turing machine that when given 0 to the power n as input outputs Cn. Okay. So, if you are given n as input in unary, so this is actually important, so n is not given in binary. So, if you are given n as input in unary, this log space Turing machine outputs Cn. So, what is a log space Turing machine? So, again just to make sure everybody understands the complete definition. So, a Turing machine of course is something that we all know. So, Turing machine is a model of computation where you have an input tape, you have finite set of states, and the machine can and there is a work tape as well, and now the machine can do some computation given an input and then accept the input or reject the input. Okay. So, now you can also think of a Turing machine with an output tape. Okay. So, suppose the Turing machine has an input tape from where it gets the input, it has a work tape on which it does its computation, and there is an output tape on which it produces the output. Okay. So, the input tape is a read only tape, you cannot use the input tape to write something or do any computation. The output tape is a write only tape, that is you can only write whatever bits you are computing or whatever bits you want to be there on the output, and you cannot read something from the output tape. And the work tape is both a read and write tape. So, basically you can do anything on the work tape. And when we talk about log space, essentially it is the space of the work tape that we are concerned about. Okay. And the reason why we are only looking at the space of the work tape is because usually the input, of course the length of the input is n. Okay. So, everything is measured as a parameter of the number of bits on the input, which is n. So, when I say log, it is log of n. Okay. So, clearly the input tape will have linear size, it has size exactly equal to n. Okay. So, if I include the input tape in the space when I am counting my space, that is kind of not fair, because you might not need that much space in your actual computation. In your actual computation you might need much lesser space. Similarly, when I am looking at the output tape, maybe you are just outputting some stuff, but you do not actually use that for your computation. Okay. So, the output tape also can have size that is linear, quadratic, or any polynomial, but you are not actually reading from that tape, it is a write only tape. So, that is also not counted during the process of computation. Okay. So, if you have actually done a course on complexity theory, these things are quite these things are of course told over there, but I just want to give a brief idea. So, when I say log space Turing machine, it is a Turing machine with a input tape, output tape, and a work tape, and I am only looking at the space of the work tape as a function of the input size. Okay. So, any questions?
So, here this unary is taken in order to make the log space log of n.
Yes.
Because if it is binary, then the log space would be log n.
Yeah, exactly. Okay. So, this is what is the log space uniform NC1, and this is we will only be looking at NC1 for the next couple of lectures. So, that is why I have defined it in terms of NC1, but you can define log space uniform for any other circuit class as well. It is the same definition, similar definition. So, why are we talking about log space uniformity? Because essentially finally what we will show is that division is not just in NC1, but is actually it is in log space uniform NC1. Okay. So, not just there is a circuit family, NC1 circuit family computing division, that circuit family can also be computed in log space. So, that is the Yeah, that is the power of this theorem.
Like all the other problems are also in log space uniform.
So, depends. So, if you can actually compute that circuit given n in unary, if you can compute the circuit, then it is in log space. So, yeah, I think most of the problems that we have seen, they are in addition, multiplication, they are in log space uniform. Yeah. You can actually generate that circuit. Okay. And the important thing, so this also I had mentioned a couple of lectures back, and I want to mention it again because this fact we will be using quite frequently, is that so when I will, so when I am, let's say when I am given the input, okay. So when I say log space Turing machine, given n in unary, of course, this Turing machine basically can compute anything. So what do, so how do I want to say this? So okay, so given, let's say, an input x, so let's say if I want to build an NC1 circuit and I am given some input x, as long as I am not looking at what that x is, okay, so what the individual bits of that x is, if I am, let's say, looking at some global parameter, or even if I am looking at n, I can use the power of log space to do any pre-computation, okay. So that pre-computation might not be in NC1, it might be in log space, but that is actually still good enough for us, because that pre-computation does not look at the actual bits of the input, okay. We will, if you are not very clear, we will discuss this again when I come to this. Okay, let me carry on. So this is log space uniform NC1. The next definition that I want to give is that of NC1 reduction, okay. So a function f is said to be NC1 reducible to a function g if there exists an NC1 circuit family computing f that in addition to the usual gates has oracle gates for G, okay. So we say that f, so okay, so what do I mean by oracle gate for G? So oracle gate for, so G is a function, okay, and G can be any function, okay, it can, let's say you can think of G as taking a string and outputting in some other string, it can be any function. So an oracle gate for G is essentially a gate, okay, which takes as input some bits and it outputs, okay, f of that, sorry, G of those bits, okay. So this you can think of as a G gate, okay. So it is taking as input some bits and it is outputting, let's say it takes some y. So this is, let's say, some y and it outputs the string G of y, okay. So this is what an oracle gate is. Now we say that f reduces to G, NC1 reduces to G if there is an NC1 circuit which, in addition to the AND, OR and NOT gates, also has these oracle gates for G. So at any point of time you can basically produce a string and you can query that is this computable in G or whatever, what is the output of G of this. Okay. Okay. So, our reduction, so when we say that these problems are equivalent, so our notion of equivalence would be with respect to NC1 reducibility. So, let us get started. So, first what we will show is that division reduces to powering. Okay. Where is circuit family computing F. So, it is a NC1 circuit family which is computing F, but in addition to the usual gates it also has Oracle G gates. Okay. So, let us look at this thing and we can see this with respect to this. So, division is NC1 reducible to powering. So, essentially what we will show when we prove this theorem is that there is a NC1 circuit for division, which in addition to AND or NOT gates, it has some gates for powering. Okay. So, there are some powering questions that we will ask and we will assume that we have those answers. Okay. That is essentially an application of this. Okay. So, how do we do this? So, we know that it is enough to compute reciprocal. Okay. So, what is the notation that I have? Okay. So, actually what we do is, what we need is, we need to compute this quantity, and actually what we need is, we need to compute 1 over y, okay, because once we get 1 over y, we can multiply that with x and get the result. So, how do we get 1 over y? So, what we will show is, we will not compute 1 over y exactly, but we will compute an under approximation of 1 over I. Okay. So, we will compute okay, let me write this. So, whatever agenda is going to be, let me write it. So, we will be computing a quantity, let us call it as y tilde inverse, okay, such that, what is the relation between y tilde inverse and y inverse? So, such that y tilde inverse minus y inverse is smaller than 2 to the power minus n. Okay. So, we will try to compute a quantity this such that this is this. Now, why 2 to the power less than 2 to the power minus n? Because once we have this, so what are these x and y's? So, x and y's are n given, so this is not 2 n bits, so given 2 n bit integers. So, x and y are n bit integers. So, the maximum value that any of these can have, for example, the maximum value that x can take is 2 to the power n. So, x times okay. So, then let me write this. So, then x y tilde inverse minus x y inverse. So, this is what I want and this is what I will be computing. What will be the difference between these two? So, multiplying this with x. So, how large is x? X is 2 to the power n. So, this is, how large is this quantity? Less than 1, yeah. So, this is less than 1, right, 2 to the power minus n into 2 to the power n, right. So, this quantity is less than 1, meaning is that it is some small. So, essentially what I will do is that, so let us say that I will call this as, let us say I will call this as t. So, essentially my answer will be, so this is actually a under approximation. So, y tilde will be an approximation of y. So, y tilde inverse will be an under approximation of y inverse. So, let us call this as t. So, the answer will be either it will be the floor of T or it will be T plus 1, okay, because the actual answer is at most difference 1. So, either it is this quantity or this quantity, and which quantity it is we can easily check. We can just multiply both these quantities with y and we can check that what is the difference between that and x, that should be less than 1. So, that is easy, but essentially we will compute this or actually we will compute just this. T is this, the approximated product that we are computing. Okay. So, we will compute y tilde inverse, we will multiply that with x, we will set that as t, we will take the floor of that, and now the actual answer will be either this or this, that we can determine just by back calculating. Okay. So, now how do we compute y tilde? So, let u be equal to 1 minus y 2 to the power minus j, where y is an integer that is less than 2 to the power j and greater than or equal to 2 to the power j minus 1. Okay. So, any number lies between two powers of 2 consecutive powers of 2. So, I just find that quantity for y. Okay. And again I can get this value of j using an NC1 circuit, because I just have to keep on dividing y by 2 repeatedly. So, basically I just have to check how many bits, I mean well, what is the position of the first one in the string y, okay, essentially that is what it is. So, I compute this value j and let us say I set y is u is equal to this. So, this implies that one minus u is equal to y 2 to the power minus j, which implies that y inverse is equal to 1 minus u inverse into 2 to the power minus j. Okay. And one more thing, just a small technicality, but it is important, is what is the smallest value of j. Okay. So, observe that here j is at least 2. Why is j at least 2? Now, that actually depends on y. So, what is the smallest y that can be there? Okay. So, note that y is greater than or equal to 2, because if y is 1 then the answer is x. Okay. So, if y is greater than or equal to 2, that is the minimum value of y is 2, then well it is between, yeah, so it is between 2 and 4. So, 2 means that it is 2 minus 1, which is 2 to the power 1 is 2. Okay. So, j is at least 2. So, we will be using this fact later on. Okay. So, y inverse is equal to this. Now, we will see what is 1 over u inverse. So, this is nothing but 1 plus u plus u square. So, this is the infinite series 1 plus u square, so on, times 2 to the power minus j. Okay, and one more observation. Uh, what is the value of y into 2 to the power minus j? Okay. So, if I divide this entire expression by 2 to the power minus j, what I get is that y into 2 to the power minus j lies between, so this quantity, it lies between half and 1, right. So, essentially 1 minus u lies between half and 1. What does it say about u? So, if 1 minus u lies between half and 1, it means that u is greater than 0 and less than or equal to half, right. So, u is less than or equal to half. So, now we can come back to this. So, what is this? So, this is okay. So, now what we do is that we will set y tilde inverse to be the first n terms of this series. So, it is 1 plus u plus up to u to the power n minus 1 into 2 to the power minus j. So, this is going to be our y. So, now you can see where we are using powering. Okay. So, essentially we are using powering to compute these powers of u. Okay. So, this is y tilde inverse, and now we can verify this quantity, that y inverse minus y tilde inverse is equal to u to the power n plus u to the power n plus 1, so on, into 2 to the power minus j. Now, each of these u's are less than half. So, I can write this as, this is bounded by 2 to the power minus n plus 2 to the power minus n plus 1 plus so on 2 to the power minus j. J we know is at least 2. Okay. So, even I take j to be equal to 2, this quantity is less than 2 to the power. So, this sum, if you just look at this sums, if I take 2 to the power minus n as outside, this is actually equal to 1 plus half plus so on. So, okay, let me write this as, okay, 2 to the power minus n, if I take as outside, this is 1 plus this sum is bounded by 2, j is at least equal to 2. So, therefore, this is less than 2 to the power minus n as we wanted. Okay.
J is 2, then it is should be divided by 2.
So, 2 divided by 2 is, it is less. So, anyway it is less than 1. Okay. So, this is the analysis. So, this is what we actually wanted. So, what we want is to have y tilde inverse as this quantity. So, now what is the algorithm? So, now the algorithm is simple once we have the analysis. So, first step is okay, compute j such that y lies between 2 to the power j minus 1 and 2 to the power j. Next step is compute u to the power, how do I get u? So, u is equal to 1 minus y. So, okay. So, compute u, which is equal to 1 minus y into 2 to the power minus j. So, we have y, we have j, so we can compute u. Third step is compute u to the power 0, u to the power 1 up to, we are going up to u to the power n minus 1. Next we compute y tilde inverse, which is equal to basically this summation 1 plus, we have seen this also, right? We have seen iterated addition also in NC1. So 1 plus u plus up to u to the power n minus 1 into two to the power minus j. Okay. Then compute t, which is equal to x into this quantity so determine which of this or is the answer. Okay, so that's the algorithm. So essentially, except for this third step over here, all the other steps are in NC1. So we have, so this is in NC1, this is just multiplication and, well, subtraction is just the same as addition. We have this is also just iterated addition, this is again multiplication, and this is again multiplication. Okay. Huh? 2 to the power minus j multiplications. No. Shifting the decimal, yeah. So it is representation of decimal numbers, representation of fractional numbers in binary. Yeah. You are shifting the decimal, yeah. Okay. So this is the only step where we need oracle gates for powering, okay, because we don't know how to do powering yet, and the rest of it is in NC1.
If we have oracle gates for the powering, how are we sure? Those oracles are, even if those oracles are computable in NC1, how are we sure that then the entire process will be NC1, because that can just.
So this you can do in parallel, na? So all these.
Sure that the oracles are in parallel.
Yeah. So here actually all the oracles are in parallel. So that's a good point. What happens, and yeah. So here actually it is just one level. Okay. So given you have these n different gates which are computing all the powers of all the first n powers of u. So if the oracles are placed in series, even then it will be NC1. So there is a proof for that. The reason is the input size for all these gates. Okay. So suppose, so let's say basically what you are saying is, suppose there is a path, okay, from an input gate to an output gate in an NC1 circuit. So this is, let's say, some NC1 circuit to an output gate, and here let's say I have several oracle gates along this path, right. Now the point is that the total length of this path is of course bounded by log n. So we can assume there are log n many oracle gates. So what is the okay, so what is the thing then? So, sorry, what is your question? If
So sir, if the log n are placed in the series and each of them is NC1, each of them is log
so,
n.
each G gate is NC1. Okay.
So now the net depth is becoming log n into log n. Like the one we did in multiplication and something like the last
Hmm.
class, for example, we did multiply.
Yeah, apparently yes, the total depth will be log square n if you don't, but I think, I don't remember right now, but I think there is a proof which shows that if these log n gates are NC1 gates, then you can show that the entire circuit also is in NC1, and that kind of, I think the idea is based on the fact that the inputs are disjoint, the inputs to all those gates are kind of disjoint. Okay. So, basically if I have log n many input gates and if each of them have depth log n, then well, the total input cannot be still more than n. So, something like that. But anyway, so yeah, I cannot comment about it right now because I have to figure out what that proof is. Okay, only then I can comment about it. But of course, this problem does not arise for us because this will only happen if these gates are in series. But here we are doing it in parallel. In fact, all the reductions that we will do, we will actually show they can be done in parallel.
What is the size of this G of y? So it can be n bits.
It can be n, yeah, it can be n. In fact, here it is taking u now. So, this gate G is taking u. So, a u is itself a n bit number, order n bit number, because it depends on y. Y is a n bit number.
To the power n minus 1 will be,
Huh?
the u to the power n minus 1 will be how many bits?
N square bits. Yeah, the outputs n square bits. Yeah, I'll try to come back to this question later on. This is a interesting question. I mean, so this is actually a general, I mean, a question about the general NC1 reducibility, but yeah. In fact, this result was actually due to Cook. This was a result in one of his papers, one of his earlier papers probably, where he showed that if you have function f NC1 reducing to G and G is NC1, then f also is NC1. So, basically the class of the NC1 is actually closed under NC1 reducibility. Okay. So, this was a result in his one of his papers. So, we have shown this theorem. So, let us move to the next result. This is also, so yeah, so essentially what is the fundamental idea in this theorem? Okay, so the fundamental idea is that I want to compute 1 over y. Okay, instead what I am computing is a quantity like 1 over 1 minus some u, okay, and show that these two quantities are kind of similar, and then 1 over 1 minus u is nothing but it can be represented as a sum of a geometric progression. Okay, so it is a geometric series. Okay, so that is essentially the idea of this entire thing. Now let us look at the other direction, that is powering NC1 reduces to division. Essentially here what we will do is that we will do the entire thing in reverse in some sense. Okay. So, what we want to compute is, given x, we want to compute the powers of x. Okay. So, let x be an n bit integer and we want to compute all the powers of x. So, what I will do is I will define a number, a large number let us call it as capital X, as, okay, let me show it pictorially first. So, I will have all the powers of x. I will start with I'll start with x to the power 0, I think. So, I will define x as being equal to, so I have x to the power 0, which is nothing but 1, then I will have x and so on. Finally, I have x to the power n minus 1. Okay. So, think of a large bit string, okay, which has all these powers of 2 and they are kind of separated. Okay. So, and we will assume that each of them are 2n square bits long. So, this I said at the beginning that any power of x up to x to the power n is at most n square bits, but I will add some extra zeros. Okay. So, basically x is this string which is concatenation of all these strings. So, now I can actually write x as something. Okay. I can write x in terms of these xi's. So, x is nothing but sum I equal to 0 up to n minus 1. So, there is a scaling factor 2 to the power n minus I equal to n minus 1, it is n minus 0. Am I writing it? Oh, 2n square into n minus I, yeah. So, 2 to the power 2 n square into n minus I times x to the power I. Okay. So, this is my scaling factor which is getting shifted and times x to the power I. Okay. Now, what is this? So, I can take the constant term outside. The constant term is 2 to the power 2n cube sigma, then I will have 2 to the power minus 2n square I into xi. So, which is sigma I equal to 0 up to n minus 1 2 to the power minus 2n square into x whole to the power I. Okay. Now, this is also a finite, yes. Thank you. Yeah. Okay. Now, this quantity, okay, is okay. So, how do I want to say this? So, essentially what can I say about this quantity? Okay. So, this quantity, so this goes to, so what happens as n tends to infinity? Okay. So, as n tends to infinity, this is a geometric series. So, this will go to 1 over 1 minus 2 to the power minus 2n square into x as n tends to infinity, right. But what I have here is not as n tending to infinity, but just the first n terms of this series. So, what I will do is that I will not care about that, I will just look at the value of this series as n tends to infinity, because beyond that the terms will be significantly small. So, what I will do is, what we can say is that x, which is actually this, is the floor of this quantity. So 2 to the power 2n cube divided by 1 minus 2 to the power minus 2n square into x. Okay. And I can write this as, so I just multiply both numerator and denominator with 2 to the power 2n square. This is not 2n cube, this is 2 to the power 2n cube. So multiply both numerator and denominator with 2n square. So I will get 2 to the power 2n cube plus 2n square divided by 2 to the power 2n square minus x. Okay. So again, so what I am trying to say here is that observe that this quantity that I am computing here is kind of greater than the actual value of x, right? Greater because I am taking some additional terms over here. Okay. But the point is that those additional terms are not contributing much, because if I just take the, because x ultimately is an integer. Okay. So if I just take those additional terms, but I take the floor, that will actually give me the value of x, because those additional terms are only going to be you can actually estimate that. Okay, you can show that those additional terms, that is if you take the terms from I equal to n up to n going to infinity, that total summation will be less than 1. You can actually again prove that, because that quantity is less than 1, I can take the floor over here and this will be actually my x that I want. So what do I have here? So given x, I just have to compute one division, take the floor of it, and that's it. I get the value of all the powers. Okay. So doing one division gives us x. Okay. So now let us move to a actual problem related to this that we can.
How do I get the power?
Now you can just read it out. So you have once you have x, you can read it out in blocks. So whichever one you want, whichever power you want, you can read out that specific block. You know that they are exactly spaced, how they are spaced out. So to get the ith power, you know you have to look at this particular position in the string. Okay. Okay. So now we will show that a special case of division can be done in NC1. Okay. So given an n bit integer x and a m such that m is less than or equal to n. That is what I have, right? Even when the following are in log space uniform NC1. What are they? The first one is computing x mod m. Second is computing x divided by m, and the third is computing x inverse mod m. Okay. Essentially what it is saying is that if the divisor is small, okay, if the divisor is m is less than n, so m is essentially a log n bit number at most, okay, then we can actually do division and all these related problems, that is division, computing the remainder of x inverse in NC1. Okay. So, why is this important? Because next class what we will show is that the actual problem, that is if I have two n bit integers x and y, we can actually break it up into smaller divisions where each of the divisors are small. Okay. Each of the divisors are some log n bit integers. Okay. So, clear so far? So, what we do here is that, so as I said, observe that, well, m is much smaller compared to x. Okay. So, x can be as large as 2 to the power n, but m is only at most n. So, what we will do is, the first step of the proof is to pre-compute some things, okay, pre-compute some quantities which are independent of x and m, okay, which only depends on n. So, what we will do is, we will, well, actually it will depend on m, but okay, I will just come to that, yeah. So, how do I denote this? So, pre-compute these quantities a to the power I, which is congruent to 2 to the power I mod m. Okay. So, once again note that because m is small, I can actually do this computation for each and every m. There are only polynomially many m's, different m's, right, from 1 to n. So, for each value of m, I can do this computation in parallel. Okay, for m equal to 1 I can do this, for m equal to 2 I can do this, and well, I will only need this for 1 m, but it does not matter to me, okay, because I can do this. And what is this computation? It is just saying that for each power of 2, what is the remainder of dividing 2 to the power I by m. Okay. So, I do this computation. And so, what do I mean by pre-compute? What I mean by pre-compute is that you can actually do this in log space. You do not have to do this in NC, because you are not using the power, you are not actually reading the input over here. Okay. So, you are just, this is a quantity which is independent of the input, okay, which will be the same for all x's of a fixed length. Okay. So, you just do this using a log space machine. But that is what I am saying. So, m actually does not matter, because m is so small, m is just log n bits, so you can actually do this for each and every m, right. So, you can do this for each and every m. So, you can think of it as follows, that for each and every m I have a different circuit. Okay. Yeah, maybe you can do this in NC1 also, but does not matter, I will do this in very easily, I can do this in log space. Okay. So, now what we will do is, we will compute the following, yeah. So, we will compute I do not have a y over here, right, yeah. So, I will compute y, which is equal to sigma ai xi. Okay. Let me just write this over here in bracket, that let x be the bit string x n minus 1 up to x0. Okay. So, x is this bit string. So, when I say xi, I mean the ith bit of x. So, I compute y, which is sigma I equal to 0 up to n minus 1 of this. Okay. What does it mean? So, it means that y is so these AIs are congruent to 2 to the power I mod m, which means that these y is also congruent to x mod m. Okay. So, why is this? Why is y congruent to x mod m? Because actually what is x? Okay. So, another way of looking at x is nothing but sigma 2 to the power I xi, right. So, this is basically the number x. Okay. So, here instead of 2 to the power I, so basically I am taking mod on both sides, mod m on both sides. So, on the left hand side, so on the right hand side I get x mod m, and on the left hand side I get this quantity y. Now, how large can y be? So, note that well, a trivial upper bound is that, so y has n many summations. Okay. So, and n, so actually n minus 1 many summation, and well, in terms of m, this quantity is, I mean m is can be as large as n. Okay. So, it is m minus 1 times each of these AIs again can be as large as m. Okay. Actually, yeah. So, actually, okay. So, this has sorry. So, what I mean is that, so the number of terms here is at most m, and the value of each AI is at most m minus 1, right, because it is a remainder modulo m, and of course, it is greater than or equal to 0. So, each xi is either 0 or 1. So, yeah. So, this is the value of y. So, now what we do is, for every t from 0 up to how long do I want to go, m minus 1, compute y minus t of m in parallel, and what do I want to output? Output, yeah, y minus Tm such that that particular y minus Tm is greater than or equal to 0 and less than m. Okay. So, actually this is very simple. The idea is that I have to compute x mod m. Okay. I reduce it to computing division with respect to y, okay, where y is a small number. That is essentially all that I am doing over here. So, from x I am reducing the problem to y, and I am proving that x mod m is the same as y. Now, I just have to check for each value of t that what is the largest value of t such that y minus Tm is between 0 and m. Okay. And essentially that y minus Tm is my remainder. Okay. So y and x are both congruent to both congruent modulo m. So essentially I have reduced the problem to y from x, and now I am just doing this with respect to, so basically now I am doing it for each and every value of t, because I know that y is small for us, y is no longer large. Okay. So now moving to the next part. So next part is again something that I will just kind of leave as a small exercise, but so once we have the remainder, how do we get the quotient? Okay. So note that, so if I have a remainder, okay, so let, if z equal to okay, fine, z n minus 1 up to z0 be equal to x. So this is a number x n minus 1 up to x0 by 2, sorry, by m, then the ith bit of z is equal to 1 if and only if twice of x I plus 1, sorry, n minus 1 up to x I plus 1 mod m plus xi is greater than or equal to m. Okay. Okay. Is this correct? Yeah. So what are we saying over here? So this is actually nothing but how long division works. Okay. So the so essentially how I get each and every symbol of the quotient. So when I am doing long division, okay, so let us say I have a number x1 to xn minus 1 to x0, it can be over, actually this can be over what do I say, I mean it need not be even a binary number, okay, it can be over any array, it can be any k array number, it can even be decimal number, but there instead of 2 you will have whatever k you are considering. But let us say you have some binary number and you want to divide it by m, okay. So the way that thing produces is that, so suppose the quotient that it produces is some zn minus 1 to z0, then the ith bit of z is 1 if and only if this is true. Okay. So basically the way it works is that you keep on looking at the difference between whatever is the product of the ith bit and your divisor, okay, you bring it down, look at the next bit and this one. So this is essentially formalization of that idea. Okay, so you can verify this yourself. Okay, you can actually go back and you can prove this. This is very simple. This is just same thing that you have learned in your school. Okay, so now once we have this, division is actually quite simple, because I have to output the quotient, and note that outputting the quotient is nothing but computing a modulus. Okay. So, the Zi is equal to 1 if and only if twice xn minus 1 up to xi, I look at this number. Okay, so this smaller number, do modulo m, add xi to it and compare it with m, and well, if it is greater than or equal to m, then Zi will be 1, otherwise not. Okay, so I can do this for each and every I in parallel. Okay, so the algorithm is do the above computation in parallel for every I. Okay. And that's it, and then you get the value of Zi. So, the last one is also similar. So, x inverse mod m is equal to, let us say, some value u if and only if is well, okay, it's equal to u if and only if x u is congruent to 1 mod m. Okay. So, I want to output u over here, u is at most m, yeah. So, I just do this check in parallel. Okay. So, algorithm is that for all u check in parallel if x times u is congruent to 1 mod m. So, multiplication we know is in NC1, and just we saw that this also is in NC1. Okay. So, that is it. So, what we are going to see next time is the following. So, we will have to try to generalize. Okay. So, all of this is with respect to a small number x and a small number. Now, how do we generalize this to a general y? So, what we will prove next time is the following result. So, given an n bit integer x and a prime power p to the power l such that p to the power l is at most n. No, sorry. So, given not n, so we will show the iterated product here. So, given n bit integers, okay, let us say x1 up to xn and a prime power p, where p to the power l is less than n. computing the iterated product of x to the power I mod p to the power L is in log space uniform NC1. Okay. So as I was saying is that ultimately our agenda is to show that we can do this computation in NC1, okay, even in general, okay, so even without taking modulo a power of prime. But what we will see before that is that if we have a power, if you have a prime power and if you want to do iterated product modulo prime power, that is actually doable in NC1. Okay. Okay, so I will stop here. So for the general proof, we'll actually, as I said, we'll break it down. So given any exercise, we'll actually break it down into smaller things using Chinese remaindering, so that you can actually represent it in this form. So this is where the number theory will actually come in.